Um, Hello, everyone, and good afternoon. My name is Viswadip Sarangi, and I'm currently a postdoc at the University of York here, and I work with Translate, who is and they invest in current medical technologies, especially here in the Yorkshire and Humber region. I work with the Cambridge University Hospitals. I work with the NHS Hospital here in the York, and I also work with Florida Atlantic University. And for the past almost 5 years now, um, we as a team, me, my research team, my supervisor, we've been working on developing technologies to identify different kinds of walking styles or gait. Those could be for a multitude of reasons. Those could be for clinical reasons. Those could be for other reasons like surveillance. Those could be for reasons related to marketing. But essentially, we're building technologies to, first of all, capture somebody's walking style and then understand or extract meaning out of what their walking is like. And the reason we know that walking conveys different sorts of information is because there's been a ton of research that has been done in terms of what we can extract from somebody's walking. We know that clinical conditions, there's a whole established sphere of clinical practices which rely on observing a patient walking, understanding what that walking means, and correlating their walking style with certain known diseases. We also know that walking is also related to somebody's emotional state. If you're happy, if you're sad, then you walk a different way. It's very, very subtle, and you really have to know what you're looking for, but it's there. And the one thing that I'll touch upon time and time again throughout this whole talk is we as humans, we are very good at understanding people's walking styles. If you've ever been to a doctor or a clinician or a hospital, you might have had this experience where the doctor would ask you to walk for a few steps in front of them. And the reason they do that is because sometimes even the doctors don't know what it is exactly that they're looking for, but just by watching you walk for a few steps, they'll be able to figure out that something is wrong or some part of your body is wrong. So it helps them home in on if it's pain or if you've had an injury or if there's a more serious condition like Parkinson's or musculoskeletal condition like osteoarthritis. But the point is that walking conveys more information that we even know or that we're even consciously aware of. The information it conveys could also be as subtle as the intent. If you see somebody hurrying towards the office, you just know that they're in a rush, they're getting late to a meeting. Or if you see somebody just leisurely walking along, or if you see somebody wanting to harm somebody else, then their walking style changes. It's not just the conscious thought or the emotion or the clinical condition that changes somebody's walking style. It's also somebody's gender. It's where they come from, or what sort of social background they come from. So there's all sorts of information that you can extract from something as simple and something that we're always seeing around us as walking style. And that is where the data science part comes in. How do you take something that is just raw data, just raw walking data, and design a technique, an algorithm, or a model that can extract meaning from just pure walking? To give you a toy example, so we know that we humans do it. The question is, how do we build a system that will do it for us? Because we humans, we have all sorts of fallacies. We get tired, our decision fatigue, we don't always make the best decisions. So making an AI or especially a machine learning model to do it would solve a lot of problems which are not just economic, but also discover more knowledge than we had idea about the fact that we can figure out from walking. And just to give you a tiny toy example of something that went viral a couple of years ago, here is Kevin Barry demonstrating 100 walks. And it seems very genuine, seems quite simple. But the one thing I want to bring focus to is it's the same person, it's the same skeleton. It's just how the limbs are moving, which is conveying so much, like a whole ocean of information, which is what me, my team, my supervisor, the whole research group has been working on, is how to translate this knowledge that we know we already have onto something that runs off of a computer. What Barry did there was extreme example of a chimpanzee walking, feminine walking, masculine walking. He does 100 walks and even more. But I'll not play the whole video, but I would encourage anyone who's interested in gait analysis to go and just watch that video, something for fun. But what we're trying to do is something a bit more subtle. We don't have extreme examples of people walking very, very differently. What we're trying to do is a gait that is not changed consciously. Barry was trying to consciously change his walking style. In our case, we're focused on developing technologies to identify differences in gait. The differences brought upon by factors that the walkers are not consciously aware of. That could be clinical conditions, that could be inherent conditions, that could be the change in emotion, but they're very subtle and they're not conscious of the fact that they have changed their walking style. And the change, the factor that results in the change of walking style is brought upon by an external factor. Could be an injury, could be the fact that they saw something horrible and they feel bad and they've changed their walking style and not even aware of it. So the question we're addressing is this, which is a very scaled down, but arguably more complex way of designing an AI solution to this problem. My name is Viswadeep Sarangi. I'm a postdoc, a research associate at the University of York in the electronics engineering department. My PI is Dr. Adar Pella. He's a permanent faculty, he's a reader in electronics at the same university. And we, for the past 4 years officially, but we've been working almost like 8 years now in developing the capture and analysis technology. And what you see here on the right side is a quick video of me walking on a treadmill or harnessed, and there's a capture sensor that you can't see right below the screen that you see there in front of me. And what the capture sensor is capturing is my whole body without being in contact with me. And this technology is very different from a lot of other technologies you might have seen where Hollywood movies put little silver balls on the body in order to track how the body moves in 3D space. This technology is very different. This is just based on the depth sensor technology, where you're not in contact. You're seeing somebody walking from a distance and you're trying to extract what the skeleton looks like. Now that that technology is established, how do you go about building an AI that gets that information? You see that the skeleton that you saw is all the AI gets. How do you take a skeleton and see a skeleton move and design an AI that can infer meaning from that sort of information? What does that model even look like? Is there any special considerations? Because if we're going about hunting for a machine learning model, there's a whole sea of models that you can start searching. Where do you even search for something like that? Is there a streamlined approach, or do you just go and hit and trial and hope one of the model works? Is machine learning model like a hammer and you just try and hit all of the nails you can and hope one of the nails just sinks into the wall? And once we have a model, how do we improve it? Sure, I mean, you can take a model and then train it on the data. It will give you some result, but how do you squeeze performance out of the model? Or are you just stuck with whatever model you have in your hand at the moment? So these are the sort of questions that I will talk about in this talk, how we answered all of these questions. And there's a few key takeaways for data scientists in the audience who are working on data sets that are similar to mine and what we have discovered in the whole process of our research. Talking about machine learning, there's a massive amount of models out there. You go on the right side, you have ensemble models, AdaBoost being the most popular these days. On the classification, you have support vector machines, decision trees, Bayesian approaches. On the neural networks, you have a whole department, a field of research that is very active in figuring out what's the best architecture of neural network that you can fit into any data set. So it's fair to say that machine learning is a very, very fast moving and very fast growing field. And it would take me years, if not decades, to try out all possible models. And I may not even come to any conclusion in a given definite amount of timeline. And I had a finite timeline to figure a solution out. So we boiled it all down to the basics, okay? Forget about all of the models. What are some basic fundamental changes between these models? There's a few different learning techniques that they use. As fancy as all of these models are, they all rely on the few crux principles. That is the learning methods. There's a few different models, there's a few different learning methods, and a lot of the models are derivatives of these learning models. The first one with being the linear hyperplane-based learning systems, which is something that the support vector machines are known for. So you have data points spread out in a multidimensional space, and you try to find the best separating linear hyperplane that can differentiate two different or more than two different classes of information. It's not always as easy as just trying to fit a linear hyperplane. So sometimes you might have to use some sort of a projection function to project it onto a higher dimensional space and hopefully find a hyperplane that is able to separate it better in the higher dimensional space. So that's one approach. We also have the information entropy reduction approaches, something like decision trees and decision forests, which are derivatives of decision trees. They work on trying to reduce ambiguity of a certain data point belonging to a certain class. And the more they're able to reduce the randomness in the data, the more they're able to make a certain data point definitely belong to a particular class, the better trained they are. And examples being ID3 decision trees and decision forests. Thirdly, we have the machine learning model that has taken the community by storm, the neural networks. There's tons of variations of this, but it all essentially boils down to being made of perceptron neural networks, which are basically functional representations of our own human neurons, and then using some sort of a loss function to calculate error, using some sort of an optimizer to backpropagate all of those errors, and then update all of the weights and just iterate the process till we have an acceptable amount of performance. All neural networks are essentially based on this, unless we're talking about spiking neural nets. And then finally, the most complicated learning system known to man, the human brain. We don't really know, not completely, at least how we learn things, but we have a few ideas, and we're going to take those ideas and try and leverage human psychology or human neuroscience to try and better these AI models along the way. A tiny little bit of detail about each of these models. I won't spend a lot of time, but I'll try and quickly touch upon what these models do and what they're good for. We have support vector machines. We know that they work on a linear hyperplane trying to separate two different classes of data. And that's what they do with or without a projection matrix. And they operate on static numeric data. What does that mean? That means you can't train them on video. You can't train them on anything that changes with time. You're sort of stuck with taking a fixed set of numbers and then hoping that the SVMs are going to learn what is the hyperplane that's going to separate these different clusters of numbers. But the basic limitation that SVMs have is they don't work well with the dynamic data. If you have any sensor that is giving you information at certain time intervals, you'll have to figure out a way of condensing all of that information into a fixed set of numbers. On the other side, we have decision trees. They work amazingly well with symbolic data. They're not geared to work with numeric data, and you're sort of stuck with only working with static symbolic data. So you have the additional problem of taking numbers and then converting them into symbols, which is great sometimes, but a lot of times you end up losing a lot of information. But the advantage of this model is it's a white box model. Unlike the neural networks, you can pry them open and see why they decided what they decided. If they decided that a certain data point belongs to a certain data class, why? Like, what made you think this data point belongs there? Then they would have the answers because the certain features had certain values, so they were a better fit for this class. So if you have a problem statement where you need to know why a machine learning model worked, then this is the ideal solution. And then we have the neural networks, arguably the most powerful of all machine learning models. They can work with any sort of data that we know at the moment, dynamic data, static data. but they are very slow to train and they require a lot of data to train. So there's a pros and cons to all of these approaches, and we tried each and every one of them. Have results that support the use of some models in some cases and not using them in other cases. And finally, the secret sauce of the whole thing, the human brain, arguably the most complex system known to us. This is the target or the holy grail of what artificial general intelligence is trying to reach at some point in the future. And as far as we know, we can work on any data. We haven't come across any data we can't train on and test ourselves on. So while we have all of these models, what do we train them on? Sure, we're trying to identify different styles of gait, but for what purpose? There's two kinds of purposes we're trying to test all of these models on. The first purpose, or the first objective rather, is intrinsic conditions, conditions that were always there. Like if we're talking about clinical abnormalities, we're talking about spastic and waddling gait. These are the kind of gait that people are born with. These are congenital. They were just there from the beginning. However, if we're looking outside of clinical boundaries, we're also talking about something as subtle as the difference between men and women. Male walking is very different from female walking. And we know this because there's a ton of research that has been done using human observers and their ability to identify a man walking from a woman walking, keeping everything else constant. Like if you normalize for height, if you normalize for everything else, there's still enough information in there that you would be able to tell a man walking from a woman walking from a very, very far distance. So these are the sort of conditions that are inherent in gait. They don't change, they're just there. And then we're talking about conditions that change. For example, emotion. If you're angry, you're sad, that changes, the emotion changes all the time. So that means your walking style changes all the time. And that is also shown in new degenerative conditions like Parkinson's or Huntington's or musculoskeletal conditions like osteoarthritis. These are conditions that people get afflicted with. They were not born with it. It was not always there, but your walking style changed somehow because of these conditions being introduced into your life. So again, just to quickly reiterate, there's two kinds of conditions, something that was always there and something which came in, changed your gait, and then went away. It could be clinical, it could be emotional. And we're trying to develop models that can identify both these kinds of situations. And there's reasons for identifying something that comes and goes, because that's a whole different problem statement altogether, and something that was just there. We know that we can do it because there's a ton of literature which says humans are very, very capable of identifying if somebody's angry or somebody's sad, if somebody's happy, and they're able to tell if somebody's a man or a woman. But what about AI? Can they do all of this? So that's exactly what we put to test. We have all these AI models, the SVMs, the decision trees, the neural networks, and then finally humans. And we wanted to pit all of them against each other. So we collected data. We asked walkers to walk on a treadmill, a speed of their own choosing, and we put a massive portrait in front of them. We had the depth sensor, which collected their data in the form of skeleton that you see on the screen. And we collected data at 24 frames per second. Each frame is essentially a single body pose. Like imagine if you're watching a video and you pause the video in the middle, that's a single frame. So we collected 24 of these frames every second. That means 24 different skeletons every second. Each of these skeletons represent 20 different joints of the human body and their 3D position in space. So if I give you 60 numbers and tell you that these are 3D coordinates of 20 different joints of the human body, you would be able to recreate this skeleton and sort of guess what the person looked like, or what his spatial orientation was in 3 dimensions at that particular point in time. And these 3D coordinates, they essentially are 3-dimensional distances from the sensor, which is taken as 0, 0, 0. So that's the definition of the data that we collected. That's the raw data. That's all we have. in terms of the models, we had to finalize exactly what configuration of models we're going to choose. As I previously mentioned, we had SVMs, decision trees, artificial neural networks, and then the human brain. But how? Like, where do we start? We know of all these concepts, but we have to code them up. We have to create these models in programming language, in Python, TensorFlow. So in the case of SVMs, we chose 3 variations. We chose an SVM with a linear kernel, with a radial basis function kernel, and a sigmoid function kernel. In the case of the decision tree, we chose ID3 decision trees, a collection of 10 different ID3 decision trees to form a random forest. And we used Gini impurity in order to decrease the ambiguity of information of which data point belonged to which class. In the case of artificial neural networks, it took us quite a while to nail this one down. And the reason is we already have 2 different static models. We have SVMs, we have decision forest. We don't need another model, yet another model, to work on static information. We needed one that worked on dynamic information. We could have chosen a multi-layer perceptron model, but we're still stuck with the problem of static information yet again. But we do know that there is a variant of artificial neural networks called recurrent neural networks that works with dynamic data. But recurrent neural networks suffers from the problem of vanishing and exploding gradients. That means, although they work really well with dynamic data, they don't tend to have a really good memory. They either forget things too fast. That means I show them a skeleton now, and half a second later, they have forgotten what skeleton I showed them half a second prior to that. Or they suffer from exploding gradients. That means they remember everything, which is great. If you have an infinite memory, that's amazing. But unfortunately, the floating point decimal only takes you so far, after which you're going to cap and reach the limits of the floating point on a computer. That means these networks remembered everything so much that it saturated their potential for taking in any more information. So we had to chuck that idea and finalize the long short-term memory, or the LSTM for short. These, did I just get a chat? Recording data. Okay, sorry, I got distracted by the chat. So these are LSTM cells, which essentially are a variant of recurrent neural nets, but they're better than RNNs. All of the layers in the LSTM cells that we chose, they were all rectified linear layer, linear unit activated. The outputs of those LSTM cells were softmax outputs, so that I squashed them between 0 and 1. And the one with the highest probability was the class that it belonged to. I used the binary entropy loss function in order to find out how far apart the real answer and the neural net's answer was. And I backpropagated all of the weights through the neural network using an Adam optimizer. And then finally, we have the humans. The only thing we made sure that the humans had good eyesight, because we were going to ask them to perform this experiment on a computer. So they needed to be, first of all, know what a computer is and not get thrown away by a screen, and that they could see. So that was the only prerequisite in terms of humans. And we put them to test, but we couldn't proceed the test yet, because all of these different models, they work on different types of data. If you remember, the raw data we had was just a bunch of skeletons put together. How are you going to feed a bunch of skeletons to an SVM or a decision forest, or to humans? I mean, humans, it was a little more intuitive, but none of these models work with raw skeleton data. So then came the process of data wrangling, or data munging, as it is more popularly known in the data science community. Fortunately for the SVMs and the RDFs, RDFs stands for random decision forests. For the SVMs and the RDFs, they work with static data, and which was fine. But the problem was, how do we take something that is dynamic and convert that into a static function? I'm sure all of the data scientists here have their own answers, because this tends to be where there's the most amount of creative expression amongst us data scientists. There's tons of ways of condensing something that varies with time into a static, limited set of numbers. But because eventually this was all going to be part of a clinical trial, we wanted to stick to something that the clinicians were happy with. So the first thing was the clinical gait metrics. These are standardized gait metrics that are chosen, tried and tested by the clinicians in the hospitals, and they represent gait in its entirety, or at least they try to represent gait in a way in which it's useful for clinicians to find out what's wrong or right with the patient. However, this is very geared towards clinicians. So this works very well in a hospital setting, but if you're trying to do something other than what will be done in a hospital, they may not have the information you want. So for that, we need something a little more generalized. For example, first order statistic descriptors like the mean, standard deviation, skewness, kurtosis, all of these standard descriptors of any sort of temporal or any sort of data set. We took the first four static descriptors and then ran them through the SVMs and the RDFs. Great, we're done with the static models. What about the dynamic models now? LSTMs. We know that LSTMs work with dynamic data anyway. So there was not much we had to do for the LSTMs. And we could just take that temporal sequence of the time series data we had and just feed it directly to the LSTMs and they would work. They're known to work on these sort of data sets. So for the LSTMs, it was home ground. It was multidimensional time series data, essentially representing gait. For humans, we went a little bit fancy. We converted all of those skeletons into what is called a dynamic point light display. And what's a dynamic point light display? It's this. It's basically a bunch of white dots moving on a black background, representing what a human skeleton would look like. And the reason we chose this representation was because most of the studies that was done in either human psychology or human neuroscience used exactly this representation in order to gain insights into how humans understand differences walking. And so it only makes sense for us to use the same representation in our own studies to be able to draw parallels between what has been done and what we're doing. Just to show you a brief example of how difficult this task is. This is a 3D reconstruction of the information that all of the machine learning models were fed. So all of them were given exactly this information in different forms, munched the data, wrangled the data in different forms that those models are happy with. But at the end of the day, this is all the information they get. And this is the same information that is given to humans. So I want to take only a few seconds to give you an example of what the walking looks like. And the only thing I ask is try and figure out if they're a man or a woman that is represented in this walking. By the way, I might want to add here that literature says we as humans should be able to do this within a second. And we're supposed to be pretty good at it. We've evolved to understand what men and women walking looks like. And hold your thought, because I'll show you the answers right now. All of the ones where you see gait pattern F is a female. The ones that say gait pattern M is a male. And these four were just randomly taken out of the data set we collected, which has got more than 50 odd walkers. And there was no hand selection that happened. We tried this with different audiences that I've given this talk to, with a random bunch of people, and the accuracy is about 50, sometimes 60, 65%, which happens to be the exact results that are quoted in literature. And when we ran the same test through all of our machine learning models, this was the result that we got. I'll draw your attention to the right side of this graph, where you see 4, 5 flat lines. So the orange one, the blue one, and the green one represent the SVM machine learning models. In the legend shown here, this one belongs to the kernel sigmoid function kernel. The blue one belongs to the radial basis function kernel. The green one belongs to the linear kernel. So right off the bat, they were able to perform really well. And this is chance performance at 50%. There's two things I want to add. The x-axis is essentially how long I exposed those machine learning models to the data set. At 0.5, we have half a second of showing them human walking. And at 3.5, I had 3.5 seconds of showing them what human walking looks like and then asking them to guess whether it's a man or a woman. And the one interesting thing, and the reason I mention it's interesting because I'll draw parallels to the human performance on the left side, is they're completely flat. They don't change with the more information you give them. They're not able to take in any more information. They're sort of stuck at whatever I just feed them in the beginning. As opposed to, on the left side, we have the humans and the LSTM performance. The human performance changes with the more information they get better, and then they get worse, and then they get better again. And the reason for this, which I'll mention in the next slide, is the human neurons, the way we are designed to appreciate motion information more than static information. If you don't see anything changing, then you feel nothing is interesting. If you see things changing, then that's where your focus goes. And I'll draw a very interesting parallel to the LSTM model here, where there's an increase of performance at 1.5 seconds, which is exactly when, on an average, people are in mid-swing phase. What do I mean by mid-swing? That means they are moving their legs really fast. So in walking, both your feet are on the ground, then they move, and then they come back static again. And then they move again, and they're back static again. 1.5 seconds is when your leg is midway in air. So you're just about to touch the ground again, but you really haven't. You've just crossed the other leg. That means there's a lot of motion in the body at that point. 2.5 is when you've kept your feet on the ground. You're about to take the next step, but you really haven't started. That means everything is static. Your body is not really moving relative to 3D space anymore. And that's when your human brain is just not interested, because there's nothing interesting there. And surprisingly, the LSTM model does exactly the same. At about 1.5, 1.6 seconds, it gets very attuned and gives a lot of attention to the data, and performance peaks. But as soon as you see the foot coming back and everything slowing down, the performance decreases. And this was extremely interesting from both a neuroscience, a human neuroscience, as well as a machine learning perspective, because that means LSTM models are what then we termed biomimetic. That means they mimic biology. And the reason for this is we're more sensitive to motion than we are to static information. For the people out there who play first-person video games, you might have seen, if you're playing Call of Duty, you see somebody running next to you, that your attention is constantly drawn towards the person running, compared to if somebody's just standing there. That's why snipers never get caught. So we are wired in a way to appreciate motion more than if nothing changes. That's great. That means I can pre-digest the information before I pass that information on to these machine learning models. Because if we appreciate it and we have a model that is biomimetic, then shouldn't the biomimetic model appreciate the same thing? So let's try this out, right? I'm not making any assumptions about biomimicry at this point. Let's just try it out on all of the models and see if it actually works. See if we can translate our knowledge of human neuroscience onto machine learning. And interestingly, I'll draw your attention to the left side of the graph here. The LSTM models, when provided with motion information, performed significantly better than the LSTM model when provided with just pure static information. And more interestingly, on the right side, these are the static models that never claimed to be biomimetic in the first place. In fact, their performance either decreased or changed in a way which was not predicted by us. So at this point, we were sure that if we're going ahead with merging the fields of human neuroscience and machine learning, these models, the random decision forests and the support vector machines, were no good. We had to stick to the LSTMs and then try and maximize performance from the LSTM model itself. We're trying to make a model. We're trying to make a model which will be used to classify different kinds of gait. At the end of the day, we're trying to form a case for us to use this model in a setting, in a clinical trial, where we will be able to use these models in a setting where you have a patient, a clinical patient coming into the hospital, deploying these models there, and then have these models give you an opinion of what the patient might have. It's also important to note at this point that we want these models to be assistive. That means we want these models to work with a human and not replace a human. These models will work well on their own, but our target is for us to provide a technological assistance to the doctors and not take the job away from doctors. And in order to do that, there's one key thing to remember, that we are not perfect. Our human brain has more fallacies and more biases than we're aware of. What we're trying to do is bring in AI to not just leverage the advantages of AI, but also try and compensate for human weaknesses. That means if there's something that we know a doctor may not be able to do as well, then we want the AI to supplement and complement the doctor and compensate for the human weakness. And the one human weakness, which was interestingly discovered in the department right next to mine in my university, is the Margaret Thatcher illusion. And what that shows, and what has been shown time and time again, is the visual cortex that we have works on something that is called a bag of tricks model. That means we don't always take in all of the information that is provided to our eyes. Our eyes constantly home in onto the maximum information features and only stick to them. So we inherently reject a lot of the information that is given to our brain, and we only stick to the parts of the image or the video that we are seeing that is most crucial for extracting information. And that means we're rejecting a lot of information which could have been helpful. And that also means that leaves us vulnerable to weaknesses that we may not be aware of because we don't know what we rejected. This was discovered by Dr. Peter Thompson in an illusion where he showed that when we're looking at somebody's face, we only see, or we mostly see, their eyes and their mouth. We tend to reject everything else. We may not be aware of this, but if there's any changes in other parts of their body, then we tend to not notice them as well as if there's a change in their eyes or their mouth. And this was more recently published and made public in Pop Culture by Huffington Post and Business Insider by showing Ricky Gervais and Adele, where it's not very obvious that their eyes and mouth have been inverted, because we expect the eyes and mouth to look that way. In fact, if you flip this image over, then Adele looks very strange because the eyes are not what we expect them to be. This is an effect known as the inversion effect, which has been well studied and well established. Well, the question that still remains is, why do we have this? Why do we have, and where does this effect comes from? And the question for me is, how does this affect my AI research? And it does, because we have this inversion effect. We not only expect faces to look certain way, but we expect people to look certain ways. That means if I ask somebody to, for example, identify somebody's gender, but I don't show them the skeleton walking absolutely upright, if they were tilted in some way, or even an extreme case, if they were flipped over, if the skeleton was walking upside down, then that completely throws away our capability of identifying anything from the skeleton. And the more you tilt the skeleton, the more it affects our ability to discern any meaningful information from this. And what is even more interesting is if you flip the skeleton completely over 180 degrees, then people are very confident of the wrong answer. So if you show them a man walking, they would perfectly identify that person as a man when the person is walking upright. But if you flip them over, then they are very confident that that person is a woman. And the reason for that is the same bag of tricks model that our brain applies. We only focus on certain tiny attributes and we try and extract as much information we can from them. As it so happens, in the case of gender, we focus on the shoulders and the hips to figure out whether the walker is a man or a woman. Men tend to have broader shoulders, women tend to have broader hips. And that's where we get most of our information of gender from. So when you flip it over, even though we consciously know that the skeleton is upside down, unconsciously, we're still expecting the shoulders to be top and the hips to be at the bottom. So that's the explanation for what happens in case inversion effect comes into gait analysis. And what is even more interesting is the LSTM share the same weakness. The graph you see here is if I train and test the LSTMs on inverted skeletons, then their performance decreases not just below chance level is at 50% here, but it decreases to a level that is very similar to humans. That means the artificial neural network variants, they share more than just a perceptron neuron with human. They actually share the weaknesses that we have. Great, we've discovered that basically AI has the same weakness that we humans do. That's not ideal, because in an assistive technology, you don't want technology and human to share the same problems. So in that case, you would get a data set, the human would identify that as a wrong answer, the AI would say the same wrong answer, and that's not good because you just end up with the wrong answer. We wanted our AI to compensate for this problem that humans have. And that means getting rid of the origin of the problem in the human brain. So humans get into this problem in the first place because we tend to reject a lot of information and only home in on certain aspects. What if we just destroyed that difference? Or what if we just destroyed that aspect and not let the AI focus on that aspect and force the AI to focus on something else? What I mean in practical terms is, what if we destroyed the anatomical differences between the different walkers? So there was no broad hip or broad shoulder to focus on. And because AI they don't know what humans look like. All they know is whatever we give them. So they would have no clue that what we're giving them does not have a broader shoulder or a broader hip. Because they just don't have any idea what humans look like. So what we did is normalize all of the limbs in such a way that men and women have no difference in their skeleton. They look exactly the same, but the motion is still there. They still move like men do. They still move like women do, but they don't look anything like men and women do. And this is a very short version of the formula that we used in order to destroy the anatomical differences between the different sexes. And this is the result that we obtained. It doesn't look human. In fact, it is not human anymore. But for the case of an AI, it doesn't matter, because if you give them human, then they would recognize what humans is. You give them this, they would just learn whatever this is. And because you have the formula, you can always get the skeleton of a human, apply the formula, get this anatomically same skeleton, and then train the AI on this and test the AI on this. The AI doesn't have to know. And the result we got was much, much better than anything we had ever tested so far. So in a combination of applying or destroying the anatomical differences and then applying the sensitivity of motion that human brain has, we were able to get a performance that was much, much higher than what we started off with. So the blue line here, the blue graph here is what we started off with, and the brown one here is what we ended with. However, this is not the golden result yet, because this is still on the vertically standing skeleton, which humans are already quite good at. They don't need any compensating. And in fact, there was only about 6-7% improvement in performance, which you can argue in the practical case may not make for that big of a difference. But the big crux of it was in the case of an inverted skeleton. The red line you see here, if you remember, is the AI that was afflicted with inversion effect. And the brown and also the orange line that you see here is what the result was after we destroyed the anatomical differences, after we made the AI more sensitive to motion. And I'm talking not just velocity, but also acceleration. This graph essentially showed that we had a case for AI compensating for human weakness. And this was the proof we needed to show that you can use AI in order to create a collaborative assistive technology, that it will work absolutely fine on its own, but we don't want it to. We want humans and AI to work together. And this was the big case we were making for a need for AI and humans to work together, because humans have weaknesses they can't get rid of. You can't just rewire the brain and get rid of the weaknesses we have, but we can use AI in order to compensate for what problems we have. So after this, that was a successful result that we had. We were able to show that machine learning model could be used for intrinsic feature classification. We improved it on upright skeleton by 6 to 7% and on inverted skeleton by 45%. And these improvements were made purely because we took the knowledge from human neuroscience and applied them onto artificial intelligence. But as a corollary, and here's something I ask everyone to just have a quick think of. What does that tell us about humans? Does that tell us anything about why we humans have that inversion effect in the first place, which has been a question which has been plaguing research for quite a while? These AI models, they don't know anything about what humans look like. And they ended up developing the same problem that humans have. Does that mean that it's just an emergent property of training? Did we develop this problem because all throughout our lives, we have seen people walk upright? We've never really had examples of seeing people walk upside down. And that also impairs our ability to identify or glean meaning from walking when people are not walking upright. Is it possible that the origin of this problem in human is experience rather than it being genetically coded into us? So this was an interesting question that came up from all of these research along with the other results that we got. We were able to publish the results both in the Frontiers of Human Neuroscience just last year, in the mid of last year, and in the Journal of Perceptual Imaging, which focuses on these sort of topics of combining AI with human neuroscience and human psychology. So we were happy with this result, but those were all intrinsic conditions. That means something that you're just born with. What about conditions that you acquire over time, which happens to be most clinical cases? What about conditions like if you get an injury and you go through a surgery? What about how that surgery is working for you? Is it actually having an effect? Is the physiotherapy having an effect? So when you're going through physiotherapy, your gait would change periodically from time to time if physiotherapy is working. And eventually, if the medications and the physiotherapy are actually doing what they're supposed to do, you will eventually come back to normal walking. So that means there's a periodic change in the same person in terms of walking style. And that's what we wanted to find out. Are these models capable of identifying a change in walking style in the same person? As an example, we have MSK conditions like osteoarthritis, but we were so happy we were still riding on the success of the intrinsic examples that we wanted to push it a little bit further. Let's say physiotherapy could take like weeks or months in order to figure out if it's working. If the model is able to identify two different walking styles in a matter of minutes, then it would be able to identify two different walking styles in a matter of weeks. So, and how do we induce different walking style in the same person without the person knowing and change their walking style in a matter of minutes? And that's when we got in touch with our collaborators out in the Florida Atlantic University, and we devised an experiment which would induce certain emotion in people, in humans, without them knowing. And we collected data in a very similar style to how we collected back in the gender study, and we changed their emotion every 5 minutes. And hopefully we would have this paper out sooner than later. And we could also prove that they were feeling sad or happy or neutral at certain given intervals of time. And the way we induced emotion was it was consensual. They knew that there was going to be an emotion study on this. It was not, we didn't ask them to feel certain emotions, but they were all visually induced in them. So in a matter of minutes, we would visually give them different stimulus in order to make them feel certain feelings in a way that had been proven to induce emotions. And the results, they were able to do it. The AI models were able to classify different models in a matter of minutes. If you give them 3.5 seconds of somebody walking, then they would be able to exactly pinpoint whether the same person at that given 3.5 seconds was feeling happy, was feeling sad, or was just neutral, didn't really feel anything. So at that point, we had a very strong case for the same machine or the same-ish machine learning model being used both for classifying intrinsic models, intrinsic characteristics like something, a problem or a difference in gait you're born with, compared to a difference in gait that has been induced upon you based on certain conditions. Could be clinical, could be emotional. But the idea was you had a same basic core model that could do all of this just the way we humans do. There's a key takeaways that I want to quickly mention before I jump to what we're doing now and what we're up to these days. Models like support vector machines and RDFs, they are amazing and they definitely have their place, but we've discovered they're not biomimetic. They don't work the way we humans do. And if you want to merge the field of human neuroscience and AI, those models are probably not the best models to go for. The models that you should be looking at is artificial neural networks, especially recurrent neural networks like long short-term memory cells or gated recurrent units, which happen to be more biomimetic than the static models. If you're working on a problem, as we were, if you're working on a problem which humans are known to be good at, like solving or finding patterns in images or gait analysis or anything that humans are known to be good at, then there's no need to reinvent the wheel and do machine learning or data science from scratch. Just learn from how your human brain does it and then take it from there. Because there's so much information in literature already about how human brain processes information that you can just take it and translate it onto an AI and it will work. So if there are any neuroscientists in the audience, I would say if you learn neural networks, especially artificial neural networks, it will give you superpowers. With your knowledge and background in neuroscience, your tangible ability to translate that knowledge using neural networks is amazing. You'll be able to achieve something that is not possible with just pure machine learning. If you come from a machine learning background, then I've fortunately had the chance of working with a few neuroscientists, clinical neuroscientists, and a few computational neuroscientists. The knowledge you get from neuroscience and human neuroscientists, especially in a clinical environment, is invaluable to improving the machine learning models that you have in hand. So I feel, and I quite believe that a combination of neuroscience and neural networks is more powerful than either of them taken in isolation. And as a general, if there's anything I figured out in terms of data science, if you're working on a multidimensional time series signal in general, that can be anything, gait signals, EEG, audio, any other sensors where you have the sensor giving you information at certain intervals in time, then do consider using either recurrent neural networks or long short-term memory cells, or gated recurrent units. They have given me the best performance. And if you haven't tried them out already, I highly recommend you try out these models. Where we are at the moment, we're commercializing the research. We're making a product out of everything that we figured out. On the right side, you will see a video of me walking on a treadmill and trying and mimicking, in a very, very bad way, different kinds of gait. And what you see here on the text is the neural network working in real time as it's getting information from my skeleton, trying to figure out what sort of a gait I'm trying to mimic. And what's interesting is it only takes a few seconds for the network to figure out what sort of a gait I'm trying to mimic. And it changes quite quickly, and it's been shown to work on we've tested it on multiple people on multiple kinds of gait, and its ability to learn how to differentiate in different kinds of gait, given all of the modifications that I've mentioned, is astounding. And we're making a product around this. So we're developing APIs, we're developing SDKs around this, and we're calling it StepSense because you make sense of steps. And this is going to be a product line to be applied in clinics, hospitals, and very recently, because of the COVID, a home-based system. So we have started clinical trials for early diagnosis of osteoarthritis in where I am in the York Hospital. We've also started clinical trials for monitoring the reduction in pain in complex regional pain syndrome patients out in Cambridge in the Addenbrooke's Hospital. And at the same time, it's only been like a few weeks since we've started the clinical trial to figure out the gait symptoms of COVID-19, which has been the hot topic everywhere, including our collaborators out in Florida. The next challenges that we have is essentially working on commercializing this research for a home-based system that can be run from smartphones or home-based technologies, which has been a massive demand from our collaborators out in Florida, considering a ton of investment in terms of post-COVID era to counter the effects of long COVID, which is long-standing problems that people who used to suffer from COVID but have now recovered, but they still have a lot of the effects that COVID has, and that's expected to last months, if not years. So having a home-based system around it to monitor, to make sure they're okay, they're recovering properly, and any medication they're given is helping them recover as fast as possible. We're also exploring more extrinsic features. We've only started off with emotion. We plan on taking it as far as possible and continue our studies on osteoarthritis and pain reduction. On a completely separate side, these machine learning models, they give us a result in terms of how much do they, So what they give us is a result of the probability of a patient or a person belonging to a certain class of gait. Like, what are the chances that you have osteoarthritis? What are the chances that you're feeling happy? What are the chances that you're a man? So because they give us a probability distribution in all of these different classes, you can use the same probability distribution to figure out how your walking is changing over time. So if you've just had an injury and you're walking exactly like somebody who would have had a knee injury, is the physiotherapy working? Is the probability of knee injury class decreasing over time? And is the probability of normal walking class increasing over time? So it just renders itself beautifully to be used in a case of rehabilitation. But I don't want to get into that. That's for another day. And yes, I think I've just about touched the timeline. So thank you so much, Callum. I mean, seriously, thank you so much, Callum. Thank you so much, the whole expertise team. And feel free to reach out to me on LinkedIn, or that's my email address up there. Dr. Adar Pella was my supervisor in my PhD and now is my principal investigator during my postdoc research here in university. And for any commercial collaborations, please reach out to him at asuta.medtech@gmail.com. Thank you. Thank you so much.